In this video, we're going to find the solution to question 2 from the structures tutorial problems. You'll notice when looking at the tutorial sheet, this question is slightly different than the others. At first glance, it may seem a little bit harder to solve, but if we follow all the same approaches as we've done throughout the other questions, you'll see that it's actually quite similar in a lot of ways, but maybe a little bit of extra work at the start. So we're given this scenario of a climbing frame with 2 children climbing on it, and these present some different forces. We've got 2 reaction forces in the structure of the frame. We've got 2 unknown forces acting down the way due to the weight of the children. And we proceed as usual. We're going to begin by drawing a free body diagram. So we'll represent the top of the climbing frame as a straight line on our diagram here, drawn in with a ruler. And as ever, to this we add all of the forces, the ones we know, the ones we don't know with the correct labels, and the distances we've been given in the question. So we can see here that we have a force of 335 newtons at the left-hand side, a force of 405 newtons at the right-hand side, and we've got 2 forces acting down the way, and we can choose to draw these forces acting down from the frame as they are in the diagram, or we can do what we commonly do and draw them on the top. It really doesn't matter as long as we don't confuse ourselves. So since we often draw it this way, I'm going to keep this style of drawing. So we're going to have a force acting down the way, which is labelled FA. And we've got another force acting down the way here, which is labelled FB. And all the distances we've been given the question as follows. From the left-hand side out to FA, we have a distance of 1.5 metres. From the left all the way out to FB, sorry, poor line there, distance of 3 metres. And from the left-hand side all the way across the length of the beam, pen will show up here, we have a distance of 4 metres. So the distance between that 335 Newton force and that 405 Newton force is 4 metres. And so far this, even if we maybe are anticipating a bit of difficulty, this should be exactly what we would do. We know we draw the line to represent the structure, we know we put our forces on, and we label the known forces, the unknown forces, and all of the distances. Now, what we've been doing in other questions is we've been asked to find the reaction forces. So we've been asked to find, these would have been called RA and RB, and we'd have known what these 2 FA and FB were. We got it the other way around this time, but we can follow a similar procedure to find it. What we must begin by doing is to pick a point where there's an unknown force. That is exactly what we would have done in the other problems. And so just to pick one, I'm going to pick the force FA. I'm going to pick this point here. And it's from this point we're going to work out all of our moments, whether they're clockwise and anti-clockwise. So rather than having the point at the left-hand side and just looking to the right, we look to the left and right to work out which of these forces are going to be clockwise moments and which are going to cause anti-clockwise moments. So we can start at the left-hand side of the beam and look along. This 335 Newton force, it's pushing up to the left. So if we imagine this pushing up and being able to rotate around the red dot, it's going to come round like this, clockwise. Imagine a hand pointing to 9 o'clock being pushed up. It's going up to 10 o'clock, it's moving clockwise. So this will be a clockwise moment here. And similarly, but on the other side, FB is pushing down the way to the right. And if this was allowed to continue and rotate around the red dot, going around our clock face, we would have clockwise motion. So we're going to have a clockwise moment here as well. And like other problems we've done, if we're pushing up and to the right of the point we're considering, this 405 Newton force would be rotate around the red point, we would be coming up here, and so it'd be an anti-clockwise moment. So again, we'll be able to label that as anti-clockwise. So we know which of our forces are going to cause clockwise moments, and we know which of our forces are going to cause clockwise and cause anti-clockwise moments. So we can bring up our formula that we use when we're doing a static equilibrium equation. We can say that clockwise moments are going to be equal to anti-clockwise moments. And all we need to do now that's different is just to take care to make sure we're multiplying the correct values together. So what clockwise moments do we have? Well, we've got one that's due to a 335 Newton force. What distance do we multiply this by? We multiply it by the distance from the point we're considering. And this distance we've been told is 1.5 meters. So even though it's pointing out in another direction, it's just in a straight line from the point we've picked. We multiply by that distance. That's 335 times 1.5. Our other clockwise moment is the force FB. So we're going to add to this FB, and we need to multiply this by the distance from our point we're considering. So this distance here. So what is this distance? Well, we're not explicitly told it, but we know it's the difference between 3 meters and 1.5 meters. And so 3 take away 1.5 is also 1.5. So it's 1.5 meters in the other direction. So this too will be 1.5. So we can write this in as well. So it's FB times 1.5. So it doesn't matter that in different directions, it's the straight line direction from the point that we've picked to take our moments about, that's point A, to where the force is applied. Then lastly, we have our anti-clockwise moment. We've dealt with the 2 clockwise. We have one anti-clockwise one to deal with. It's a force of 405 newtons, and we're going to multiply this by the distance from, again, our point at A to where this force applies. So I'll pick a different pen color here, use purple. The distance is this distance here. Now we know that the distance up from the left until point A is 1.5 meters, and the whole beam is 4 meters. So the remaining distance, the purple line I've drawn in here, must be 2.5 meters. And so that's exactly what we multiply the 405 by, 2.5 meters. And what this left us with is a formula that we can calculate some parts of. It's going to leave us with one thing we don't know, the force at FB. And as we've seen before, this is exactly what we need in order to find the other missing force, but we can balance our vertical and our vertical forces up and down after this. So let's have a look at this calculation then. So first of all, with 335 times 1.5, and that's going to be 502.5. We don't know what FB is, so we can just write that down as 1.5 FB for the moment. And on the other side, we'll have 405 multiplied by 2.5. And that gives us 1012.5. This means that 1.5 times FB is equal to 1012.5 minus 502.5. We subtract 502.5 off both sides. So 1.5 FB is equal to, now do this just now, equal to 510. And that means to find FB by itself, we divide both sides by 1.5. So 1.5 FB divided by 1.5 is FB, and that's equal to 510 divided by 1.5. Which is 340 newtons. And we can have a quick look at this thing. Does this make sense? Well, it's a positive number, so it's possibly a real force. The 2 upward forces were 335 and 405, so it makes sense that it's somewhere in that region as well. The other force, FA, is going to be similar, but not the exact same size. So it's a sensible sounding number. We should always go back and check our working, but we've got no reason to believe that anything's wrong here. So with that in mind, we can now use the other equation of static equilibrium we have at our disposal, which is that upward forces are equal to the downward forces. Now we were told in the question, we have 2 upward forces. They're equal to 335 newtons, and let's check that again, make sure I put in the right number, 405 newtons. And they were equal to 2 downward forces, which at the beginning we called FA and FB. So 405 plus 335 is equal to 740. And on the other side, we don't know FA, but we've just worked out FB 340. So FA is going to be equal to 740 minus 340, which is equal to 400 newtons. So there are our two answers. We got FB was equal to 340 newtons and FA was equal to 400 newtons. And so we have solved the problem.